Hello, everyone. Okay. Hello, everyone. Thanks for being here. Let me remind that we are recording this, so if you don't want to appear in video, that's the good time to show up. Although for the moment, I don't see any other people beside us online. Let me introduce our first speaker of today, who is Professor Weiwei Xu, who kindly agreed to give a seminar for us, even if he is now in China, where it's past midnight, so it's already the following day. So let me introduce him. So Dr. Professor Weiwei Xu is a professor at Shanghai University and also has a joint affiliation at the Shanghai Institute of Advanced Technology. He received his PhD in 2014 from the Institute of the High Energy Physics, Chinese Academy of Science. Then he worked just across town at MIT from 2014 to 2019 as a postdoctoral associate and subsequently as a research scientist. Then he joined the Alpha Magnetic Spectrometer, also known as AMS, experiment in 2011. And he took his current position in China in 2019. Where he's been continuously working on the AMS experiment. And today he's going to talk us about the latest results from the Alpha Magnetic Spectrometer experiment, AMS 02, I think, right? Just the latest ones. Thank you so much for being with us. For yours.
Should I proceed?
We can hear you.
Yes. Can you hear me?
Yep.
Okay. Thank you, Federico, for introducing me and also for inviting me to give this seminar. So let me just get in the topic of my seminar. So AMS is an experiment on the International Space Station to study the physics of dark matter, antimatter, the origin of the cosmos, and search for new phenomena through the precision, long-duration measurement of charged cosmic rays. As we all know, charged cosmic rays, when they enter into the atmosphere, it interact with this material and produce secondary particles, so-called air shower. But the properties of charged cosmic rays cannot be measured or studied on the ground, like the charge sign and the magnitude of the charge and the momentum of this particle. So to measure cosmic ray charge and momentum, it requires a magnetic spectrometer in space. So that is what AMS is doing. AMS is a large international collaboration, and we have about 50 institutes from 15 countries. And the institute which I'm in, SDIAT, is located in this part of China. So cosmic rays has a very long history of research. It was discovered in about 120 years ago. And before AMS, there were many experiments measuring the cosmic rays either from balloon or from satellite. And this result agree with experimental model, with the theoretical models, mainly because the error was large. Now with the precision measurement from AMS, which show different result compared with earlier measurement, and apparently this result cannot be explained by the current models. So AMS is a space version of a precision detector which were used in accelerators. When I first joined AMS in 2011, I was impressed by this kind of detector, which we typically use in the accelerator physics, can be integrated in such a small experiment like AMS to be operated in space. So from AMS, there are several detectors, like the transition radiation detector on the top of the AMS. It identifies positrons and electrons, and it has 9 layers of silicon tracker. One is on the very top of the detector, and we have 7 layers in the magnetic ball and 1 layer at the very bottom to have a maximum, has the very long lever arm to extend the energy range. So it measures the charge and the momentum of the particle. We have a ring imaging Cherenkov counter here. It has 11,000 photosensors to measure the ring produced by the Cherenkov photons. So it measures the charge and energy of the particle. In the bottom is the calorimeter, which measure the three-dimensional shower shape, therefore to determine the energy of the positron and electrons, and also separate them from the hadronic showers. So we have two banks of time flight. One is at the top, called upper top, and another bank is at the lower top. Together, they measure the charge and energy. And we have the permanent magnet, which used to bend particles in different ways to identify positive and negative charged cosmic rays. And surrounding this inner ball of the magnet is the anti-coincidence counters to reject particles coming from the side. So basically, we are detecting charged cosmic rays which come from the top of the detector to the bottom. So with the combination of different detector technologies, we are able to identify matter and antimatter and measure all the cosmic ray species. I will not go through all the details, but for AMS, we have redundant measurement of many fundamental properties of the particles, such as the momentum, the charge, rigidity. Rigidity is a word we use in AMS very often. It's the momentum per unit of charge. It's intrinsic value for a magnetic spectrometer. And we have energy measurement, and also we are typically measuring the flux, which is number of particles in this unit. So AMS was launched to space in 2011, and since then we were continuously taking data, and we foresee an upgrade of the detector to be happen in 2025. And this upgrade is to add a new 8 square meter track layer 1 and layer 0 on the very top of the detector to increase the acceptance to 300%. And this was to cover the whole acceptance of this detector. So in this talk, I will show you the latest result based on the data collected from 2011 to 2022, about 220 billion cosmic rays in total, and also some projections when we run in the detector with an upgrade to 2030. So today I will basically show part of MS result. First is the precision measurement of cosmic ray nuclei. This is a spectrum of the charge distribution for different elements in space. You can identify all these elements from hydrogen up to iron and nickel. So the separation achieved by AMS between the hydrogen and helium is better than 1 in a billion. So this is a very accurate detector to measure the charge distribution. And also, when we go to higher charge, like for iron and copper, the separation is better than 1 in 100. And this is mainly due to the low abundance of heavy elements like copper. So in cosmic rays, basically we have our result can be summarized in 3 aspects. The first is the primary cosmic rays. The primary elements like helium, carbon, oxygen, and iron are produced during the lifetime of the stars through the nuclear synthesis. And they are accelerated by the explosion of stars, like supernova. And these elements are called primary cosmic rays. And we have found that with the precision measurement of these species, the primary cosmic rays, they have at least 2 classes. Here, what is shown in this yellow is helium, carbon, oxygen, and iron. So you see that with after different scaling factors, the spectrum shape of these 4 elements are identical. And another 4 elements, neon, magnesium, silicon, and sulfur, they form the second group of primary cosmic rays. We also found that secondary cosmic rays also have 2 classes of this kind of rigidity dependence. So what is secondary cosmic rays? They are produced by the collision of the primary cosmic rays with the interstellar medium when they propagate in the galaxy. So like lithium, beryllium, boron, and fluorine, they are secondaries. And indeed, all these elements on Earth is produced by the cosmic ray collision. So we have found that the lithium, beryllium, and boron, they have identical rigidity dependence above 30 GeV. And also lithium and beryllium, the normalization is different by exactly a factor of 2. And recently, we have published the result of the fluorine measurement, which is much lower abundant, apparently. And the rigidity dependence is different from the light secondary cosmic rays, lithium, beryllium, boron. So they form a second group. And we have also discovered a third group of cosmic rays, nitrogen, sodium, and aluminum. These three elements are partially primary and partially secondary. The first impression, if you plot the rigidity dependence of all the cosmic ray species, you can see that these three elements are located in between the primary cosmic rays and the secondary cosmic rays. So from this shape, we guess that these three elements are indeed the combination of primary and secondary. To have a quantitative measurement, this we fit this spectrum by the combination, linear combination of secondary and primary. So for nitrogen, the primary component is this spectrum shape is taken from oxygen, and for boron, this spectrum shape is taken from the secondary cosmic ray shape is taken from boron. As you can see, this combination can fit the nitrogen spectrum in the entire energy range from 2 GeV to 2 TeV or 3 TeV. So this fit in the entire energy range is something surprising. And eventually, we go to higher charge. We found that this sodium can be fit by the combination of the silicon spectrum and the fluorine spectrum, and aluminum, and again, by the combination of silicon and the fluorine. So you see that this spectrum are indeed both, these elements are consist of both primary and secondary components. And even more surprisingly, so we have a new and unexpected observation. Traditionally, these elements, carbon, neon, magnesium, and sulfur, are thought to be primary cosmic rays. Namely, they are just produced in the stars. But with the high precision, we found that these four elements are not pure primaries. They all have a significant secondary component. So this is carbon. It can have, if you fit this spectrum, it has a significant component, which can be described by the boron spectrum. And for neon, magnesium, and sulfur, the same case. But if you compare the even Z nuclei and the odd Z nuclei, and you can see that they have distinctly different primary and secondary composition. For even Z nuclei, carbon, neon, magnesium, and sulfur, even though they have a small contribution from secondaries. But for the odd Z nuclei, the nitrogen, sodium, and aluminum, the secondary component is much more abundant than the even Z nuclei. So what this method also has an important implication. This is a model-independent way to measure the relative abundance at the source, namely before the cosmic ray propagation. So currently, with the available data from AMS, we have determined that the abundance ratio of carbon to oxygen, neon to silicon, magnesium to silicon, sulfur to silicon, nitrogen to oxygen, sodium to silicon, aluminum to silicon. And this abundance are independent measurement, which does not really depend on the propagation of cosmic rays. Also, there is an important implication. For people who are doing the cosmic ray propagation, there was a long-standing idea that carbon is a pure primary and boron is a pure secondary. Therefore, this B/C ratio has been used extensively in all the series of cosmic ray propagation. But now, since we have with this precision measurement, we see a tiny contribution from the secondary carbon. So carbon is not pure primary anymore. So the question is how to use this B over C ratio correctly in any cosmic ray models. I think this is an important point to notice for all the theory calculations. So now AMS has measured all these elements which I show in this color histogram, but I didn't have time to go through all of them. But there are other elements which I show in white color, and these elements require more data to have accurate measurement, mostly because they have a very low abundance. Let me give just one example. It's on the origin of the heaviest cosmic rays. And this is the binding energy as a function of atomic number. For different elements, there have been some common understanding that they come from different history of the cosmos. For example, iron is the heaviest element which produced by the stellar nuclear synthesis. Nickel and zinc is the lightest element which produced by supernova explosion. So the question is, are they different? So to answer this question, AMS has a preliminary measurement of the nickel flux, and the current data shows that the nickel, indeed, it has a quite similar spectrum compared to iron. And if you fit this with a linear function, it can be fit by a constant value. Now, by 2030, we'll provide a much more comprehensive comparison among these elements, including zinc. And now let me share you the latest result on positrons, electrons, and antiproton. So this is a very simple cartoon of the origin of this element. Like from cosmic collision, they produce positrons and antiprotons. From dark matter, you can also produce electrons, positrons, and antiprotons. And from pulsars, they can produce equal amount of positron and electrons. And sorry, there's a chat, something in the chat. Anyway, this is latest result from AMS on the positron spectrum. And you can see this is for the first time. And with high accuracy at high energy, we can determine that the spectrum changes their shape. And indeed, the fluxes drops off at high energy. And to describe this shape of the spectrum, we have developed an empirical function which carries the information that we have the contribution from collisions at low energy, this gray part, and the contribution from a source. And this source could be a pulsar or dark matter. But the important point is that for this source, it needs a cutoff at highest energy. And this is a new observation. So currently we have a significance of 4.7 sigma, and with the central value of this cutoff energy around 750 GeV. As time goes on, we are going to extend the energy range of this measurement, and by 2030, we will go to 2 TeV and reduce the error by a factor of 2. And this will allow us to precisely measure whether the positron spectrum, the highest energy, goes back to the prediction of purely cosmic collision, namely the contribution from dark matter or from other sources diminish here. And we have also measured the antiproton to proton flux. And currently, this flux ratio shows that above 60 GeV is energy independent, namely constant. And this is the model prediction from Jonathan in 2016, and generally predict a decrease in behavior as function of energy. And more surprisingly, experimental point of view, that we have seen the similarity in the antiproton and the positron flux, and this is shown here. So this similarity is very important to understand the origin of the positron excess, since the antiprotons cannot be produced by pulsars. Their mass is much heavier. And by 2030, AMS will greatly improve the accuracy of the antiproton spectrum, and will help us to identify the origin of the positrons. Now let me get to the last spectrum, which I'm going to show, is about the electrons. And this is the first time we see an indication of a source-like term, a source term like positron in this electron spectrum. So the current electron spectrum can be fit by a power law at low energy and a power law at high energy, plus an equal amount of electrons and the positrons here. So this is to identify, to fit this, show the spectrum change at TeV region. And by 2030, we will extend to further to 3 TeV. And this will help us to have a 4 sigma identification of the source contribution at its highest energy. This is particularly important because for these new, say the sources like dark matter or pulsar, they basically produce equal amount of positrons and electrons. So in 12 years, AMS has published all the results in physical review letters. We have just one accepted a few weeks ago, and we will submit more on the antiprotons and isotopes. It is very important to note that for AMS, more than half of the paper was selected as editor suggestion. So let me come to the summary. AMS is a unique position to provide data to create a definitive theory of cosmic rays. And in the first 12 years, none of the results were expected. And based on this experience, with the upgrade of the detector, we can anticipate new surprises. Okay, that's it.
Yeah, thank you so much. Okay, do we have any questions from the people in person? Not yet. Let me ask one. So in the first part about the primaries, the presumed primaries cosmic rays elements like carbon and others, can you use the fraction of secondaries that you infer from your fit to determine some properties of the propagation in the galaxy, so to infer something about the models of propagation?
Okay, this is a very well. This is a question which I think I will try to answer you, but maybe not to your perfect. So the idea is that here we are using the say the pure experimental spectrum shape of primary. And for example, for carbon, we use the primary spectrum shape from oxygen and a secondary from boron. And this fit over the entire energy range indicate that this secondary carbon, they have the same origin as the secondary boron. So okay. I don't know whether this has important implication for the cosmic propagation, but it's a kind of common understanding that carbon, this secondary carbon, should be produced like the mother part from the collision of the mother particle, like oxygen.
Mm-hmm. Okay. All right. Other questions here? I don't see anything online. Nope. All right. Okay. Let's thank Weiwei again. Thank you.
Thank you.
And let's now move to the second speaker. Okay. Do you want to?
Yeah, I'm gonna try to fix this. Okay.
I think so. Yeah.
Okay, I think. All right. So our second speaker today is Amir Sharon, and he obtained his Bachelor of Science in Physics and Electrical Engineering from Ben Gurion University in the Negev. Following that, he pursued his Master's of Science in Physics at the Weizmann Institute of Science under Doron Kushner, where he continued as a PhD student. And now he's going to be graduating soon from his PhD, and today he'll be talking to us about gamma ray deposition histories of supernovae.
Yeah, hello everyone. So yeah, before I start, just wanted to say that these are difficult times for me, and I wanted to express my solidarity with the victims and their families of the Saturday's attack in Israel, and for the people that are kept hostage. May they return safely and quickly back home. Right, so yeah, let's start.
Studies.
Okay, so what are supernova? Supernova are exploding stars. And what do we observe? So mostly at optical wavelengths, we observe this. We observe a point in the sky. It turns brighter, in this case about 20 days after the explosion, and then it decays. We can't see it anymore. And this is very bright. It can shine as bright as a whole galaxy, right? And we also see this. So this is the Chandra X-ray observations for the Milky Way of the famous Tycho supernova. And still 400 years after the explosion, still there's still hot gas there. And the distance that this remnant encompasses means that the velocities are very high. They are about 10,000 kilometers a second. So what do we know about supernova? We know generally they're divided to two types, core collapse and type 1a. Core collapse comes from massive stars, and type 1a from white dwarfs. So they're found core collapse in star-forming galaxies. That's because the massive stars die young. They're not found in early type galaxies. And type 1a are basically found in all types of galaxies because there's white dwarfs everywhere. And the ignition mechanism is the gravitational collapse of this core of the massive star. And for type 1a, it's the thermonuclear binding energy. All right, so okay, we know several things and many things actually, but we still don't know many basic things, like how do they explode? So if we take type 1a, we know there's a white dwarf, but what ignites him? We still don't know. We also know in which exact systems they explode. So going back to the type 1a, if something ignites it, then what is it? Is it another white dwarf? Is it a main sequence star? Is it a triple system maybe? Still don't know. And there are other types of supernova, it's a whole zoo actually, like calcium-rich, superluminous, which we even know less about. And there are models for each of these supernova. So let's show one of them. So here I show you observations of a type 1a supernova. It's an underluminous type 1a. And a model, Chandrasekhar mass white dwarf explosion. And the comparison here is between the B-band light curve and the spectra, something like 10 days after the peak light. And it seems like there's a good match here, right? In both of these observations. But are the calculations done in this modeling, are they robust? Does it show what it's supposed to? And this is not trivial. Modeling supernova is hard. And in fact, we'll see that this model is actually very far away from the observations when we look at the correct parameters, observables. So why modeling supernova is so hard? Let's talk a little about this. Modeling supernova is done usually in the following steps. You take a star and you determine the initial conditions either by hand or by some stellar resolution code. And then you explode it. And you evolve the explosion with the hydrodynamics and the other complicated physical processes like nuclear reactions, maybe neutrino transport, general relativistic corrections, could be asymmetry in the explosion, so maybe turbulence, very complicated. But I'm not going to discuss this further. And you evolve the explosion until the material is freely streaming, so it doesn't interact with each other anymore. And you're left with the ejected a profile for this ejected material. mostly what's more important is the density profile and the composition. And this takes usually a few hours until it's freely streaming. And then light is created in this ejected material. It interacts with it and escapes it until it reaches our observatories. And to model it, we use optical radiation transfer, right? And it turns out that this is also very difficult. And why is that? Mainly because the opacity here, which quantifies the interaction between light and matter, is very uncertain, because the material here is usually made from has iron group elements, and these have a large number of atomic lines, and the opacity is made from these lines, so we need to know them, and we actually don't really know them well. There's a large inaccuracy, or sometimes there's just we don't know all of these atomic transitions. And these transitions belong to a certain ionization and excitation level, which is also uncertain because not that long after the explosion, the material departs from local thermal equilibrium. So to determine the ionization levels, we need to take into account the ionization and recombination processes, and these are also not known to good accuracy. And even if they do, it's very hard to calculate. So radiation transfer codes that do this, a non-LTE code, they're so heavy they can't deal with more than 1D simulations. So what happens is that there are many radiation transfer codes, and they have large disagreements for the same initial conditions, same initial profile. And what we want to do is find a way to bypass these complicated calculations. So to do that, we need to talk a little about how the supernova are powered. So what powers them, at least for most supernova, at least at late times, is the decay of nickel-56. So nickel-56 created during the explosion. It's radioactive, so it decays into cobalt and then iron. And in this decay, energy is released in gamma rays and positons, but mostly gamma rays, about 97%. So if this was true, we would naively expect that at late time, when the ejecta expands sufficiently, so it's optically thin, meaning that energy is no longer trapped, so the luminosity will be equal to the instantaneous energy generation rate. But what we see that it's not the case. We see that the observations decay faster than the energy generation rate, which is the dashed line right here. So what happens here? What happens is that not all the gamma rays deposit their entire energy to this ejecta. Some of them begin to escape. And so to account for this, we add this deposition fraction, which is denoted in FDEP. And when we take this into account, we can reproduce the late time light curve. So this is the solid line here. But how did we do this? How did we know what is exactly this deposition fraction is? So we know that at early times, the ejecta is optically thick, it's very dense. So everything is trapped, the gamma rays are trapped, and it equals 1, and the lines coincide. At late times, when the ejecta is sufficiently optically thin to gamma rays, we can assume that the gamma rays collide once with the ejected material, and we neglect multiple scatterings. So the deposition fraction will be the chances of a gamma ray to collide times the average energy that's being transmitted. And this is similar to the optical depth. So it's like the opacity times density times distance. So this goes like the column density, and so it goes like t to the -2, and the proportionality constant is what we call t0 squared. Okay, so t0 is roughly the square root of the opacity times density over the velocity squared, and we can think about it as a time when the ejecta transmits from being optically thick to optically thin. Okay, and here the opacity is the gamma ray opacity. This is important. We'll see soon enough. And lastly, at intermediate times, we interpolate between these two behaviors of the deposition being 1 and going like t to the minus 2. So in this case, we use this interpolating function. It behaves correctly at both regimes. We have another parameter n to tune this interpolation. Okay, so we can do this fit now and find the escape time. In this case, it's 36 days. It's typical for type 1a supernova. If I forgot to mention, I think this is a type 1a supernova. And we can find the nickel mass because, like I said, this supernova is powered by nickel, so this controls the luminosity of this light curve. And we can do this. So we saw that we can do it find these parameters quite easily for an observation of a supernova. But what's the advantage of this method is that we can do it easily to the models, unlike this radiation transfer. So we don't need to do actually optical radiation transfer at all. We can do simple gamma ray radiation transfer and find this parameter for the models. And gamma ray radiation transfer is easy. And that's because the opacity that was so hard to calculate for optical light is very easy to calculate for gamma rays. And the opacity here is just Compton scattering, mainly. And Compton scattering, it's simple. We know analytically the cross sections. And because the energy of the gamma rays is much higher than any other energy of the system, like the temperature, or any ionization energy or something like that, we just don't need we don't care. We don't need to know them. We just care about the number of electrons in the wave. So now we can find these observables for both models and observations and compare. So what did we do? First, we got a sample of volumetric light curves. So this is actually the downside of this method because the supernova here have to be very well sampled, both in time and wavelength. In time because we look at late times, and in wavelengths because we need the entire volumetric luminosity. So we need also IR observations, which are not always available actually. But a large fraction of the flux goes into IR, so we insisted on that. We can also correct for a missing IR flux, but this adds another uncertainty. Then we can calculate these observables for a supernova sample, right? The nickel mass, the escape time, and then compare two models. So let's look at some results. First, this is the results of the sample of supernova. So we have several types of supernova. So there's 1A, the blue ones, there's core collapse, so there's stripped envelope, and type 2P. There's also other peculiar types like calcium rich and 2000 FG like. So these are superchandrall 1As. We can already see that each type has their own characteristic values here, right? Own region in this diagram. So we can sort of classify the types here. But now let's look at models like I promised. So first, type 1A. So here we focus on the type 1A supernovae, but notice that the axes here are flipped. And we see already that, okay, the nickel masses here, they have a large range, like an order of magnitude between the faint one and the most luminous one. And the escape times have a more narrow range, right, between 30 and 45 days. And we can also already see that there's a clear positive correlation between the mass and the escape time, the nickel mass and the escape time. Now let's add the models. So here they are. We have transosecular mass explosions, subtransosecular explosions, and collisions of two white dwarfs. And we see that none of the models really work here. They don't really reproduce this relation. And some of them have a negative correlation between the nickel mass and the escape time. This is the most pronounced for the Chandrasekhar mass explosions. Now, you remember the model I showed you at the beginning that was quite okay, right? So this is one of these points at the top right there. So very far away from the observations. So yeah, some work needs to be done here. So moving on to stripped envelope supernova. So this is again focusing on stripped envelope supernova, but flipped back the axis. The escape times here are larger. They're between 80 to 150 days, I think. And now when we add models, we have a large span of escape times. This is because these models have a large range of parameters like the explosion energy, the ejected mass, and we can now constrain these parameters or rule out the range of parameters that don't fit within this diagram. We can focus on a specific supernova and even have tighter constraints. Next are calcium-rich supernova. So these are a very mysterious, relatively new kind of supernova. They're faint and rapidly evolving, and their location here in this diagram is sort of between the stripped envelope and type 1A. They sort of connect these two distributions. Whether this is a coincidence or something, indication of something, we don't really know yet. And now let's look at models. So these are right there. Since we don't know what these really are, the models are very, very different. We have helium shell detonations on white dwarfs. So there's a helium-thick shell and it detonates, but the core remains intact. There's a merger of a white dwarf with a hybrid white dwarf. There's an ultra-stripped star. So we see very different models. What's common to all of them is that they disagree with the observations. They all have very short escape time. This is because they have low ejected masses. So some of these models, like the helium shells, have only a few tenths of a solar mass ejecta. And this is not enough to reproduce the escape times that we see. And the reason I think is that because they're rapidly evolving these supernova, so their models are built that way, that they would create this rapidly evolving nature. But the rapidly evolving means that the rise time is short, or the decay time after peak, not the late time light curve. But when you look at the late time light curve, which I think is more robust, then you see that they're not that fast. They have typical 1A values, if not higher. So these models should take this into account. And lastly, I want to talk about the 2000 FG-like supernova, or the Super Chandra 1A. So, okay, as implied by their name, they're very bright. So they have large nickel masses. What's more surprising is that they also have high escape times. So they sort of continue this trend of the regular type 1A supernova of being more massive and more higher escape times. So now let's add models of these. And again, none of the models really fit here. So they either have sufficient escape times, but not sufficient nickel masses, like the white dwarf mergers here. Or they have, they're bright enough, they have high nickel masses, but they're too fast. Their escape times is too low. So these are the magnetized white dwarf and the high mass collisions. Although now or my advisor is doing this high mass collisions, and we try different combinations of masses, and we think it's very preliminary that we sort of starting to get there. So this is a collision of a 1.2 white dwarf and a 0.8 white dwarf. So it's a good direction to investigate. All right, so to conclude, I showed you that the gamma ray escape time is useful to constrain supernova models. We got some nice results. The first is that the type 1A supernova models Basically, they will fail to reproduce the observations. Calcium-rich models also disagree with the observations, and that the super Chandra 1A have high escape times, and also the models should also work to agree with the observations. Thank you.
Okay, questions? Do you have any questions? Oh, sorry. Okay, great talk. My question is, what should I exactly take away from the diversity we see in the escape types? You know, it's some degenerate function of like ejection mass and opacity of those gametes. What's actually the diversity?
So the opacity is the same. That's yes. It's just decay of nickel and cobalt. So this is fixed. What changes is the mass and the energy and the distribution, to a lesser extent, the distribution of the nickel in the ejecta. So the more centered it is, the higher escape times, because the optical depth will be higher on average. If it's more, you know, more spread, more mixed, then yeah.
Any other questions? Oh, yes.
Can you think of any or describe some selection effects that may be present in the samples that you can?
Yeah, so okay, the sample is not meant to represent the actual distribution. It's not complete by any way. For example, the type 1A here, there are many more events here in this region. We actually have another project of doing this luminosity function of type 1A. And there are many more events here than here. So yeah, just what happened to be followed and had good observations. I guess bright ones are a bit biased, especially in the thinking type 2P, for example. So in type 2P, we need very long observations to measure any escape time. So I don't think I can measure escape time of very low luminosity ones.
Yes, I'm wondering if you can think of any selection effects that you would like reduce, for example, for type 1As, reduce the number of low nickel mass, but long.
I don't think so, actually, because you mean maybe there are. Yeah, I'm wondering with you.
Models typically go in the direction, yeah, right? So they predict.
You know, you're saying maybe there could be here,
Yeah.
over here.
Yeah.
I think we would have seen them, because I think it's also known that these low luminosity ones are fast, not just in the escape times, also in their rise times and their decline rate, right? The delta M15, whatever. So I don't think they're really supernova in these missing regions.
Any other questions? Okay, we actually have to end a little early today because there's a meeting right afterwards. So I'm just gonna end it here, but please feel free to sign up to speak with Amir. And let's thank our speaker again. Great.